Hello everyone. Welcome to the first lesson in College Calculus 1. Before we begin, we're going to be doing a review. But before we even begin that, I actually wanted to briefly talk about one thing I've noticed a lot of times when viewing people learning and or teaching things like college calculus or introduction to statistics, which is I want you to know that what we're doing is not easy. So if you feel like you're struggling with the material, know that you're not alone. Right? It seems easy when somebody with years of experience is teaching it and everything makes sense when you're following along, but then you go to do it yourself and suddenly things don't work out. This is not unusual. In fact, most people struggle when the topic is new to them. For example, I actually struggled with college calculus whenever I was an undergrad. But then over time, using it, doing things like physics classes, beginning to teach, things like that, it's all become secondhand to me. So I actually tend to teach it where I'm going to be doing very specific steps every single time. Whereas once you feel like you have a good enough understanding, you might just skip a lot of these steps. Most people do. But I wanted you to be aware that the reason you're going to see me a lot of times say what rule we're using for every step, it's because I want this to be accessible to anyone as they're on their learning journey, and know that, again, just because something has clicked with you, someone else may still find it difficult. And I really want to have these building blocks set up so that somebody could follow along and hopefully it'll start to sink in and make sense to them. So now let's look at our review. We're going to first start by looking at some things we're going to be using a lot in calculus, that we're going to be looking at a few things just so that everybody's on the same page. This may be relatively new to you, it may just be a quick refresher, or this might be something that you really are fine with and you don't really need to follow along with and you can jump straight to the chapter 2 material. So first let's talk about functions. So a function f is a rule that assigns each element x to a set D, and exactly one element, f of x, in a set E. The set D is called the domain of the function. So this would be, for example, what are the values that when you plug x in, what outcome do you get? What are the possibilities? So this would lead to your possible values, which would be your domain. The number f of x is the value of f at that x. So for example, if you ever see f of x, what this is saying is that you're taking this x value and you're transposing it onto some new set of values, right? So you have some x, and it's saying, what is this value once the function has acted upon it? The range of f is the set of all possible values of this f of x. So where the domain is all of the possible values that your x can be, right? So it might be something like, this can be any value from 3 to 7, where 3 is not included and 7 is. Your range is going to be, once this function has acted on this x, what are the possible values you can get? For example, maybe something like every value from negative infinity up to positive infinity. The domain of f is either given, or it's usually going to be all real numbers, which we write like this. It's a double line R, for which f of x is defined. So that is to say, usually we're going to have something like this. X is going to be all real numbers. Or you might have some restriction based on specific values we cannot put. For example, if my function f of x was equal to 1 over x, this would mean that x can be anything except 0 because we can't divide by 0. In this case, you would have a different domain for this function because I can input any positive or negative value except 0. So how do we represent functions? Well, there's 4 main ways we can do it. The first is verbally. That is the description in words of what the function is doing. For example, it doubles whatever is input. This would be a function where you take whatever input, let's say it's 4, and you double it. You can do it numerically, which is to say you'll have a table of values. You could do it visually using a graph, or you can do it algebraically, which is where we're going to have some explicit formula, which of course this is what we're going to be using mostly in this course. So now let's talk about some of the notation we're going to be using in order to define our intervals that we talked about earlier with things like domain, range, things like that. So for example, you're going to have less than or greater than. And in interval notation, these would be represented by either an open parentheses, which means that it's at that value and above, but not including that value. Or you could have an open parentheses at the end, which represents that it is less than that value. It's up to that value, but not including it. You could also have less than or equal to, which we represent as a square bracket, which means that it is every value bigger than this value, including this value. And we have greater than or equal to, which is a closed square bracket, which means everything up to that value, including it. So examples of this might be something like from -3 up to +4. So this means that it would be all the possible values from -3, so -3, -2, -1, 0, 1, 2, 3, 4. And it's every value from -3 up to 4, but not including either of those values. So the way we would show this is whenever you have this open parentheses, when you're actually showing it on an interval, you would use an open circle. This represents that it goes up to that number, but does not include it. Whereas in the square brackets, might be something like, I'm going to make it a little bit smaller in this one. Let's say that we had -1 to +2. So similarly, if I have an interval representing this, I would have -1, 0, 1, 2. And I show this by putting a closed circle. And this just means that it's every value from -1 up to +2, where -1 is included and +2 is included. So what about if we have something that is a little bit of both? Well, you can actually mix and match these. For example, you could have something like -2 up to +1. And in this case, it's everything above -2, not including it. So -2, -1, 0, 1. So we'd put an open circle. Up to 1, which is included, so we put a closed circle. Now, you may not always have both an opening and closing depending on what the specific interval is. For example, right now we looked at two values that's greater than this and less than this, or greater than or equal to this and less than or equal to this, or greater than this but less than or equal to this. But what about if we had something like x is less than 3? So in this case, if we were to draw it out, let's say we have 0, 1, 2, 3. Well, because this is not equal to, it means that it's everything that is less than 3, but not including it, so it's an open circle. And then I'm just going to go all the way off. And if I wanted to turn this into interval notation, I would have to consider, well, if it's going off in the negative direction and it just keeps going, there's no end point to it, this means that it goes to -infinity. Now, anytime you have infinity or negative infinity, you will always use parentheses because there is no end point to it, right? We're not getting to infinity or negative infinity. We're approaching going in that direction forever and ever and ever. So that it's from negative infinity up to 3. If we had something like x is greater than or equal to -2, it'd be the same idea. We have that this is -2, -1, 0, 1, 2, and it's everything greater than, but also including -2 to the right. So if I wanted to write this as interval notation, this would be square bracket -2, because this is my starting point, and then I'm going off to infinity, which again will always be parentheses. And then last, let's look at one more example where we have -6 is less than or equal to x is less than 5. So if I were to draw this interval, I'm just going to kind of skip all the numbers in between, but let's say this is -6, this is 5. Because this is greater than or equal to, this -6 is included. Because it's less than 5, this 5 is not included. So I would have a closed circle on -6, I would have an open circle on 5. And then writing this in interval notation would be, because the -6 is included, it'd be square bracket -6 up to 5 parentheses. Next, we're going to talk about another type of function you might encounter, which is called a piecewise function. So a piecewise defined function is defined by different formulas for different parts of our domain. That is, our different x values. So let's say, for example, you had the absolute value of x. Now, absolute value just takes any value and it makes it positive, meaning that we're going to actually look at two different parts of this. We're going to look at when x is positive, and we're going to look at when x is negative. And pretty much what this is saying is if x is greater than or equal to 0, we just put x, right? So if I say 3, which is greater than or equal to 0, I get out 3. If I plug in 0, well, because this is greater than or equal to 0, I just get out 0. Now we need to look at what happens if x is less than 0. Well, what this is saying is that if x is a value that's less than 0, I need to take whatever that x value is, and I need to take the negative of it, meaning that, if, for example, if I had negative 3, so negative 3 is less than 0, I plug this in, negative 3. So whenever you have a negative and you take the negative of it, you get positive 3. So you can see that this is actually a piecewise function. We have to consider what happens at each part. So now let's look at what it would look like if we graphed this. Well, if we graphed this, right, we have our axes. And when x is greater than or equal to 0, meaning starting here, if I plug in 0, I get 0 out. And what's happening is as it goes up by 1 in the x direction, it goes up by 1 in the y direction. So it's going to look like this. Oops. Now, what happens with my negative values? Well, as my x goes into the negative domain, my y values will be the positive equivalent. So this is what our absolute value would look like, both as a piecewise function, right? So if we have an x that's greater than or equal to 0, we leave it. If we have x that's less than 0, we change it to a positive. And then this is what the graph would look like, no matter what value I plug in. If I plug in a 1, I get out a 1. If I plug in a negative 1, I also get a 1. Because what's happening is it's taking any of these values, which if we weren't inverting it, it would look like this. Whereas x went to the negative, y would also be negative. What we're doing is we're saying, okay, take that value and make it positive. Next, we're going to look at function symmetry. So if you have a function that this is true for all values of x, where f of x, so any value x I plug in, would be equal to the same function with any values I plug in for negative x, this is considered an even function. So if every x I plug in the domain, this is true, this is called an even function. So an example of this might be something like f of x equals x squared. So if I plug in negative 1, I get out negative 1 squared is positive 1. If I plug in positive 1, 1 squared is positive 1. If I plug in negative 2 squared, right? So I'm squaring a negative, so it's negative 2 times negative 2 gives me 4. If I plug in f of 2, I get 4. If I plug in f of negative 3, this would be 9. If I plug in f of 3, this would be equal to 9. So this is called an even function because anything that happens on the negative values in this case would also occur for the positive values. They're going to be equivalent. So this is an even function. So this means that it has symmetry. Kind of like when we were doing the absolute value, right? If I plugged in 1, I got 1. If I plugged in negative 1, I got 1. If I plugged in 4, I got 4. If I plugged in negative 4, I got 4. So they end up with the same values, so they're equal to each other. So these are even functions. Odd functions, on the other hand, are whenever, if I plug in some negative value of x into my function, this would be equivalent to plugging in positive value into that function, but it would be the inverse of it. It would be opposite of it. So for example, if I plug in f of negative 1, this would be the same thing as taking f of positive 1 and then just taking the negative of that. So an example of this would be the function f of x equals x cubed. So let's say, look at it. If I plug in 2, I get 2 cubed, which is 2, 4, 8, so I get 8. If I plug in f of negative 2, this would be equal to -2 times -2, which gives me +4, times -2 gives me -8. So it's the same value I got when I plugged in positive, but the negative. Same thing if I plug in f of 3. This would be 3 times 3 is 9, times 3 is 27. If I plug in f of -3, this becomes -3 times -3 is +9, times -3 gives me -27. So you'll see that these values are equivalent, except for it is with the negative in front of it. So whatever you get for the positive, you get the negative of that same value. So you get the same magnitude, but the positive is one direction, positive or negative, and then the negative would be the opposite. So when looking at these, if you wanted to think of it graphically, your even functions are functions that are symmetric about the y-axis. That is to say, whatever is happening on one side, let's say you have something like this, would be symmetric across the y-axis, meaning that you could almost think of it like they're a mirror image. Whatever's happening on the positive is also happening on the negative. If we were looking at the odd functions, these will be symmetric about the origin. That is to say, if I have a value that goes like this, then it's sort of like I'm flipping it over the origin. It would look like this. If I had a value that was going over here, it would go down here. If I have a value that's, let's say it's growing this way instead, something like a logarithmic function. Well, in this case, if I had an odd function, it would look something like this. So it's symmetric about the origin, which is to say, right here. You could think of them as mirror images across this. Or you could think of it like rotating it 180 degrees, right? So if I have something like this, where it's going like that, by rotating it 180 degrees, it's doing the same thing, but on the opposite end. A function is called increasing on an interval if I plug in some value x1, if it is less than plugging in x2 into that same function. So this would be an increasing function if this is true on some interval. So what this pretty much means is that if I had something like this, if I plug in x1, let's say I have a value here, if I plug in x2, because it is greater than whatever output I get, it would be greater than. It could be anything here, then this would be an increasing function. A decreasing function would be when I have that f of x1 is greater than f of x2. Now notice in this, both of these, I have f of x1 is less than f of x2, and for decreasing, I have f of x1 is greater than. Notice that there's no equality in this. Now there is actually a term for things like that, which would be non-decreasing or non-increasing function, which means that basically if it were non-increasing, it would mean that it can go down or it can stay the same. If it were non-decreasing, it would mean that it could go up or it could stay the same. So it's increasing if this is strictly true, that if I plug in one x value, as I move my x value higher, my function would also have an output that is higher. A decreasing function would be as my x value increases, my y value that I get would decrease. A non-increasing function would mean that it can go down or not change, and a non-decreasing function would mean that it could go up or not change. So in that case, you might have something like this, where maybe you have an x here, it can go up, it can go up, it can stay the same, but in the end, it cannot decrease. Next, I want to talk about the difference quotient. Now, this one is actually pretty important because we're going to use it a lot in this course. But the difference quotient is that you have f of x plus h minus f of x divided by h. And what this means is if I have some function, let's say that I have my xy axis here, and I don't know, let's say this is what my function looks like, something like this. What the difference quotient is saying, that if I have some value x, this is my outcome from my function, whatever the line tells me, right? So if I were to come over here, I would get some value. And then I have some new value, which has a difference of h. So we'll call this one x1 and this one x2. So what we're looking at when we look at the difference quotient is what is this value here? And we're saying, okay, if I take the outcome at f of x and the outcome at f of x plus h, what is the difference between those two, which means what is the difference of your actual output. So this would be f of x plus h minus f of x. And then we want to divide by the distance that we've traveled. So basically we're looking at how far is our distance between x1 and x2. And really all this is telling us is it's just giving us our slope and the difference formula, right? If you think about if you wanted something like, the distance between 2 points, x1, y1, and x2, y2, what would we do? We would take the change in y divided by the change in x. That's all this is. In this case, it would be y2 minus y1 over x2 minus x1. Well, in this case, h is the difference between x2 and x1. The top, the y values, are the difference between whatever outcome you get, which we'll call y2, minus y1. So it's really just taking the difference for each of these data points, and then from there, we can figure out what the slope is between them. Something like that. Let's do some examples to test out what we've looked at so far. So let's say that we have the function f of x equals the square root of x plus 5. And we want to know what is the domain of each of these functions. So if you remember, the domain are what values that can x take, where I would get some output. So because this is under a square root, we know that this term has to be greater than or equal to 0, right? I can have the square root of 0, which would give me 0, and I can have the square root of any positive value, but I can't have a negative. So pretty much what we have is that this x plus 5 must be greater than or equal to 0. So then what I'm going to do is I'm going to subtract 5 from both sides, and I would get that x is greater than or equal to negative 5. So what does this mean? It means that I could plug in negative 5, and I would get negative 5 plus 5 is 0, square root of 0, good to go. I could plug in a value that's greater than negative 5. So if I plugged in negative 4 plus 5 would give me positive 1. Square root of 1 is 1. Let's say, for example, I plugged in negative 3. Negative 3 plus 5 would give me positive 2. Square root of that would give me square root of 2. So this means that I can plug in any x value starting at negative 5, including negative 5, and up. So writing this as an interval would be square bracket negative 5 up to infinity, because I can plug in any value that's larger than or equal to negative 5. The next example is, what if we have the function g of x, which is equal to 1 over x cubed minus 9. Now, whenever you're doing the domain of a function, generally what you're looking for is not what values you can plug in for x, but what values you cannot plug in for x. Now, based on this, is there anything that I can't have? Well, I cannot have a 0 in the bottom. So pretty much what we're saying in this case is that I cannot have x cubed minus 9. Oh, sorry. This should be a square. X squared minus 9 cannot be equal to 0. Well, then what would make that equal to 0? So let's find out. So we go x squared minus 9 equals 0. So then I just add 9 to both sides, and I get x squared equals 9, which means that I cannot plug in. So what would make this true? It would be that if x is equal to 3, or if x is equal to negative 3. Meaning if I plugged in 3, 3 squared is 3 times 3 is 9. If I plug in negative 3 times negative 3 gives me positive 9. So these are the two values that x cannot be. X cannot be equal to negative 3, and x cannot be equal to positive 3. So these cannot be true. So then if I were to write my interval, this is going to end up, first of all, looking like this, where I have every value except negative and positive 3. So I'd put a circle over each of these, but otherwise everything else is shaded in. And if I wanted to write this in interval notation, this would be every value from negative infinity up to negative 3, but not including negative 3. And then I would use a union to connect the next part of the interval, which would be starting at negative 3, but not including it, up to positive 3, but not including it, And then last, union positive 3 up to infinity. And this would be the interval for all of the values that I could plug in for x in this function, which would be pretty much anything other than negative 3 and positive 3. Now, what about this function? We have h of x, some function h of x, which is equal to 3x plus 5. So as I said before, we first want to look at, is there anything that we can't plug in that would cause it to have some sort of issue? Well, in this case, no. We can plug in anything. So this means that it's all real values. So if we were to draw this out on our number line, it would be everything. Or to write it in interval notation, we would have every value from negative infinity up to positive infinity is fair game for this function. And in one last example on domains, let's say that we have y is equal to the natural log of x plus 2. So as before, we have to consider what values a natural log can take. So a natural log can be any value that is greater than 0. Because if you were to graph out a natural log, it looks kind of like this. Meaning that it will approach 0, but it will never touch it. Meaning that whatever is in here can go approaching 0, but it can never be 0. So we'll have x plus 2 must be greater than 0. So again, we're just going to figure out what value makes this true. By subtracting 2 from both sides, we have that x must be greater than negative 2. So if we were to draw this number line out, if we have negative 2 here, it is not included because it's greater than, not greater than or equal to, and it's everything to the right of negative 2. Next, we're going to do an example looking at using the difference quotient. So let's say that we have the function f of x is equal to 9x minus 5. So in this case, we have our f of x. Now, if you remember, our difference quotient was f of x plus h minus f of x divided by h. So in this case, we already have f of x. We need to figure out what f of x plus h is. Now, the way you do this is whatever is inside the function, you just replace with x. So in this case, it would be 9 times x plus h minus 5. And then we're going to distribute our 9. This is going to be equal to 9x plus 9h minus 5. So this is our f of x plus h. This is our f of x. Now let's plug them into our difference quotient. So this is going to be equal to 9x plus 9h minus 5 minus f of x. So we're taking the negative of this. So this is going to be minus 9x plus 5. Now, this is all divided by h, and we're going to do some cancellation. So minus 9x is going to cancel with positive 9x. Minus 5 is going to cancel with positive 5, and we're going to be left with 9h divided by h. The h's will cancel, and we'll be left with 9. So the difference between f of x when it's 9x minus 5 and f of x plus h, again for the function 9x plus 5, would end up being a difference of 9. For the next example, we're going to look at this function here, f of x equals x over 4, but we're going to look at it specifically at the point 2. So we're going to say when x is equal to 2. So in this case, we're going to plug in 2 for this, it would be 2 over 4. And then if we were to find our f of x plus h, this would just be, again, we plug in x plus h wherever there's an x. So this would be x plus h divided by 4. And then again, because we're doing it at x equals 2, we're going to replace 2. So this would be 2 over 4. And this one would end up being 2 plus h over 4. So we're doing this at f of 2 and f of 2 plus h. So now if we were to do this into our difference quotient, f of x plus h, we had that this is equal to 2 plus h over 4 minus f of x, which we just said is 2 over 4, and then we divide the whole thing by h. Now, because these are fractions in the top here, and we're adding or subtracting them, this means that they have to have the same denominator. Well, they do. It's 2 plus h over 4 and 2 over 4. So in this case, it becomes 2 plus h minus 2 over 4 divided by h. So now what happens, we have 2 and minus 2, so these are going to cancel. So we have h divided by 4 divided by h. So the next thing we're going to do is we're going to consider that this h is kind of the same thing as h over 1. So we have a fraction divided by a fraction. So when we're doing fractional division, what we do is we multiply by the reciprocal. So we take this value here, and it kind of does this. This h comes to here, this 1 comes to here. So this becomes h times 1 is just h divided by 4h. So then we cancel those. We're left with 1 over 4. So what's happening is that when we have this f of x, which was x over 4, at point 2, if we go up by some amount h, we will go up by amount of 1/4. So whatever value we plug in as h, it will be 1/4. So if h is 1, we go up by 1/4. If h equals 2, then we go up by 2/4, and so on. For our last difference quotient example, we're going to be looking at the function f of x equals x squared plus 3. So again, looking at our difference quotient, we have f of x plus h minus f of x. We have f of x, so we need to figure out what is f of x plus h. So we do f of x plus h. Anywhere we have an x, we plug in x plus h. So this becomes x plus h squared plus 3. Now we have x plus h squared, so what we're going to have to do is we're going to have to FOIL this out, which is first, outer, inner, and then last. Or you could think of it like this, right? If we have x plus h times x plus h, we're going to multiply the first terms, then we're going to do the outer terms, then we're going to do the inner terms, then we're going to do the last terms. That's what FOIL means. So this ends up becoming equal to x squared, x times x is x squared, so outer x times h, so plus xh, inner x plus h, and then last. H times h is h squared. So then this means that our f of x plus h is x squared plus, in this case, 2xh plus h squared, and then of course we have to include that plus 3 that we had there. So now we're going to plug these in to our difference quotient. So what we have is f of x plus h, we said was x squared plus 2xh plus h squared plus 3 minus our f of x. So minus x squared minus 3. And this is all divided by h. So next thing we're going to do, we're going to look see if there's any cancellation. Well, we have positive x squared, we have negative x squared. We have positive 3, we have negative 3. This leaves us with 2xh plus h squared over h. So now what we're going to do is the fact that both of these terms have an h in them, we're going to pull an h out. So this is going to be h times 2x plus h, and this is all still divided by h. These h's will cancel, and we'll be left with 2x plus h, which means that our difference between our x values is going to be 2 times whatever value we plug in for x plus our difference, our h here. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.